Cubaan 1, 2, 3. Okay, Assalamualaikum and a very good morning. Okay, today I would like to continue on the second topic in our course, which is on the equilibrium. Again, my name is Dr. Muhammad Afiq Muhammad Uri. Okay, let's continue. Okay, here's some quotes. Okay, without faith, whatever you do will not be meaningful. However, with faith alone, also you will not able to move forward. Okay, equilibrium is the key. Okay, entahlah siapa kan yang bagi ni. Okay, so kalau you buat sesuatu lah, walaupun you berjaya everything, tapi tak semestinya benda yang buat tu meaningful lah. Okay, sebab tu we need to have faith. However, kalau you ada faith alone pun, tak semestinya you be able to move forward. Okay, contohnya macam you rasa okay dengan kepercayaan you boleh kenyang, tapi kalau you tak suap dalam mulut you will not be able to feel full lah. Okay, so equilibrium is the key lah. Equilibrium is the key. So let's ponder upon it. Thank you. Okay, next one. Okay, this is for the part A. Okay, I will divide this topic into two parts, which is the part A and also part B. Okay, right, here is the outline for part A. Okay, we will focus on the definition and concept of equilibrium, is including what is equilibrium, why equilibrium, why we need to study equilibrium in this course, the type of equilibrium available, okay, which is type of equilibrium is specifically related to our study. Okay, we need to look to that as well. And then we need to question, does it mean that the maximum extraction is achieved at equilibrium? Does it mean that the maximum separation is achieved at the equilibrium? Okay, so we need to question that. Okay, then we need to learn as well on the partition coefficient or distribution coefficient. Okay, so there are two kind of distribution coefficient, okay, or partition coefficient. Okay, they denoted as K. Partition coefficient as Kp, distribution coefficient as Kd. Okay, later on we will learn to that, but don't worry, so we go slowly one by one. Definition and concept of equilibrium. Okay, so now let's look on what is equilibrium. Okay, what is equilibrium? The first, when the rate of the forward reaction and the rate of reaction are equal, the system in dynamic equilibrium. Okay, so what happened that, for example, you have two phases. Okay, and then you are separated by probably membrane over here. Okay, and then you have what we call a partition over there. All right, so you have part A and part B, or we can call as phase A and phase B, and then you have particle over here, and then you have particle over here. Okay, so when the rate forward reaction, for example here, it goes forward and then it goes backward, the rate, okay, the rate of forward reaction or the rate of movement, okay, are equal. Okay, the rate of forward and rate of reverse reaction, okay, are the same. Okay, so they are in equilibrium. Okay, so this does not mean that nothing is happening. So it doesn't mean that nothing is happening. It doesn't mean that it stopped. Okay, so it's like a continuous process. Okay, right. So if you look in the figure over here, okay, the rate of in same with the rate of flow. Okay, so it doesn't mean that nothing is happening. Okay, same goes over here where the down escalator, somebody goes try to go upright because they have the same rate. So even though they are, it's like that the position is not moving, but actually there is something happen over there because the person is trying to running and then the escalator is moving down, but the position of the person is fixed over there. Okay, because they have the same rate. Same goes to the chemistry. For example, the evaporation and condensation rate is equal, so it doesn't mean that nothing happened. So how the image present dynamic equilibrium? Okay, that's okay. I already explained it to you. Thank you. Okay, now let's go for the next. Okay, the next thing that we need to learn is why we need to learn equilibrium, especially in the separation. Okay, you can read all these things. okay, by yourself, but I would like to explain. Okay, during the separation, so we actually try to create at least two faces. Okay, so maybe here one or two faces. Okay, so in this example, for this example, here is liquid and above one is the gas phase. Okay, below one is liquid phase and the above one is gas phase. For example, in liquid, you would like to try to separate alcohol. You want to what you call extract alcohol. You want to analyze what type of alcohol. For example, okay, in the real situation, even in Malaysia also, okay, because of alcohol intoxication, especially when they try to produce their own alcohol beverage, they want to what we call put extra flavors, so they put some things that produce methanol, okay, instead of ethanol. In alcohol, usually we consume ethanol, not we lah, the person that consume alcohol usually consume ethanol. But if okay, something wrong during the production, or is the production method is not right, or they try to adjust, okay, to their as to improve the addiction, okay, so maybe the creation of methanol will occur. Okay, when that happen, methanol can intoxicate you, so it is actually dangerous, and a lot of number of cases, person death due to methanol intoxication. Okay, so we need to be okay. That's the example lah. That's the example that I can give you. Okay, for example, you would like to study about the methanol in the alcohol beverage. So what can you do to separate, okay, that particular alcohol from the liquid phase? Okay, as you know, the boiling point of the alcohol is much more lower than the water, right? So what you can do that you can create the gas phase. So what can you do? You can apply some heat, so you can produce some gas over there. So your alcohol, which has the lower boiling point, will be evaporated to the upper space. Okay, so in the equilibrium, especially in separation, actually two or more zones are created lah, because we want to extract our analyte from the initial phase to another phase. Okay, so the preferential distribution of different components involved in the process in each zone. In above the example, the gas phase is richer in alcohol than the mixture. So here, okay, we need to look at the preferential distribution. For example, if we heat at a certain temperature, okay, so we know that at the gas phase, okay, will be preferred by the alcohol. For example, I'm not really sure, methanol maybe at 60 degrees Celsius start to boiling, so they will go to the gas phase because they prefer for at the gas phase. Okay, by choosing the condition, one phase is enriched while the other is depleted in some components, or it means that few. Okay, for example here, okay, by choosing the condition, okay, for example, okay, here, all right, after a certain time, okay, the gas phase, okay, it will get reached by the methanol, okay, after certain time, okay, until they reach the equilibrium. Okay, so I need you guys to understand, it doesn't mean that in equilibrium, okay, I need to really stress about it. It doesn't mean that in equilibrium you will get the same amount of analyte, okay, at both sides. Okay, let's say you use 50-50 ratio of phase. Okay, it doesn't mean that. Okay, right, equilibrium mean that the forward and reverse reaction is at the same rate. Okay, for example, there are only two components over here. Meanwhile, here we have 8, but the equilibrium mean that they have the same forward and reverse reaction, or forward and reverse movement. So it doesn't mean that, okay, again, it doesn't mean that equilibrium that both zone have equal phases. Doesn't mean that. Just mean that the forward and reverse reaction is the same. Okay, alright. So, alright, the maximum pressure is reached at the equilibrium distribution of the component, but in practice, pressure may fall short of this as equilibrium is not attained lah. Okay, that is different story. I don't want to go into that later on. I don't want to go into that for the time being. Okay, we will discuss. Okay, either our extraction process is achieved at the equilibrium or not. Okay, right. So let's move forward. Thank you. Okay, so now let's look on the type of equilibrium. We do have three type of commonly known, okay, in equilibrium. Okay, is including the solubility equilibrium. Second is phase equilibrium, and the third one is chemical equilibrium. Later on, I will explain to you, okay, how to differentiate between them. Okay, right. Okay, so the first one, solubility equilibrium is a dynamic equilibrium between a solute and solvent in a saturated solution in a closed system. Okay, so for the solubility equilibrium, okay, is involve a saturated solution. Okay, you have the undissolved solute, and then you have a solution. Okay, over here. Okay, I should move around my mouse. Okay, we have the undissolved solute, and you have the dissolved solute. So because of the movement forward and reverse here is the dissolve and undissolved process occur at the same time, so we call that as the solubility equilibrium. Okay, so it must be in the saturated solution. Okay, alright. Okay, that is for solubility equilibrium. How about phase equilibrium? Okay, phase equilibrium, a dynamic equilibrium between different physical state of a pure substance in a closed system. Particle in both phases gaining or losing kinetic energy such they are moving from one phase to another. Okay, so you doesn't need to remember every of thing specifically. So what you need to explain that in the phase equilibrium, two or more phases are created, and then particle, okay, inside here, okay, gaining or losing kinetic energy, or moving forward or moving backwards at the same reaction. Okay, at the same rate of movement lah. Okay, so that's, even if you can explain that, it's already okay for me. As long as I can understand what you're trying to explain, it should be okay. Alright, if you look over here, the water in the closed system, we have the gas phase and also we have the liquid phase. So if you look over here, at the certain time we have the same moving forward and moving backward, or gaining kinetic or losing kinetic, they are at the same reaction. So when that happen, we call that we reach the phase equilibrium. Okay, and then the third one is the chemical reaction. Okay, a dynamic equilibrium between reactants and product of chemical reaction in closed system. Okay, chemical reaction equilibrium, okay, is when you perform the chemical reaction. Condition is in the course of a reversible chemical reaction in which no net change in the amount of reactant and products occur. Okay, for the chemical reaction equilibrium to achieve, the reaction must be reversible. Okay, if the reaction is one way, so we cannot achieve the chemical reaction equilibrium. Okay, when is it we supposed to have the chemical what is the example, okay, of the chemical reaction equilibrium? For example, you do the titration. Okay, when you achieve, okay, before you write the color, supposedly you supposed to achieve the equilibrium. It means that if you put maybe from acid to base, change color from blue to pink. Okay, maybe just if you put a little bit to base, it change to pink. If, for example, you put a little bit acid, it goes back to the original color. So that is how the example that I can give to you about chemical reaction equilibrium, where you achieve that the amount of reactant and products occur the same. Okay, no net change in the amount, but there are still a process, like I said to you, the process of going forward and going backward, but there is no net change, okay, in the reactants and products. Okay, now let's go for the next slide. Okay, why I focus on the phase equilibrium? Because in separation, okay, phase equilibrium is the type of equilibrium that actually involve the most. It means that the separation ended. Okay, if we reach the phase equilibrium, okay, we reach the maximum, okay, separation, okay, on that particular system when we reach the phase equilibrium. Okay, for example, okay, you want to extract on the second phase over here. Okay, this is the first phase. When we reach the extraction, we reach the end of the separation when we reach the equilibrium. But it doesn't mean that, okay, later on I will discuss it doesn't mean that we get a optimum extraction, because it doesn't mean that at the equilibrium that we have much particle inside on the second phase over initial phase. Okay, it doesn't mean that. Okay, so you need to choose the right system for you to achieve the maximum, or not the maximum, the optimum extraction. Okay, alright. So I think we already described. Okay, we have in the phase equilibrium we have at least two phases. Okay, so we have the first phase, and then we have the second phase. And then, for example, if you have particle in here, and then you have particle in here, equilibrium is reached when rate of A migrating equal to rate of B migrating. Alright. Okay, I think it's a little bit confusing lah. Okay, unless A1, B1, and like in phase 1. I think it's a little bit confused lah over here. Okay, maybe you can write over here is A not B1. Let me try to B. Okay, A. What you need to understand from this figure that A and B is referred to the same analyte lah. Refer to the same analyte in here lah. They are not different one. Okay, they are the same one. Okay, so you can imagine that A go to A2. I think here is A1 as well lah. Why they get? Just put here B lah. Okay, just to make we understand better. Okay, so I change to A over here and B. So no A1, no A2. So equilibrium is reached when rate of A migrating equal to rate of B migrating lah. So A, B to A. So when we have that same rate of migration, okay, so we achieve the phase equilibrium. So the next question we need to ask ourselves, does it mean that the maximum extraction and okay at the equilibrium? Okay, so my answer to this question, okay, you need to ask among yourself. Maybe we should discuss, no need lah, I think I will discuss again in the class lah later if you don't understand. Does it mean that the maximum extraction and at equilibrium? Okay, think about it. Right, so in a closed system, the separation end, okay, reach maximum separation after the system reach the equilibrium. Okay, it means that the separation ended. Okay, maximum extraction, okay, when we reach the equilibrium, nothing change at all. Okay, you wait until tomorrow, okay, the particle distribution will never change. Okay, will never change. Okay, even you wait until tomorrow. However, optimum extraction, why I say optimum extraction, that in our extraction, if we want to obtain a very good extraction, it means that we try to get all particle on our desired phase. For example, the second phase is the one that we want to extract. Okay, so you have the extractant solvent over here, you want to extract everything, so you want to have the optimal extraction. So that is different story. Okay, right. So optimal extraction is different story, since depends on the favorability particle distribution of targeted components in that particular system. So depends on the favorability, okay, or depends on the system that you trying to introduce. To determine the system effectiveness of separation, ratio concentration of targeted components lah, okay, between two phases can be calculated. Okay, so right now the system I refer here, okay, is it's like that you has two different system that have two different solvent. Okay, so two different solvent, that is the type of system that I try to mention over here. Okay, it's not that I try to refer that they have different volume or they have different pressure. Okay, that is different story. Okay, because that is actually part of Le Chatelier principle, the one that can affect the extraction. Okay, that is different story. I'm not really sure if we will touch into that in this course. Okay, I will check on that. But in this particular system that I refer to, for example, you have two different system. Okay, for example, you have here is the water. Okay, Okay, and then what here is hexane. Okay, you want to extract, for example, benzene. Okay, benzene is kind of toxic chemical. Okay, for in Sungai Kim Kim, is contaminate Pasir Gudang River. So one of the component lah found as the component that contaminate that Sungai Kim Kim River lah. So for example, you have H2O over here, and then you try to extract using CCl4, carbon tetrachloride. Okay, so you try to extract, right? Okay, so in this particular system, I specifically, okay, refer to two different system of different solvent, not different volume lah. Okay, that is the different story. Okay, so to determine the system effectiveness, okay, which one, for example, which one is more effective, this one or this one? Okay, let's say they have the same ratio of volume. Okay, so the we can calculate the partition distribution, okay, or this partition coefficient or distribution coefficient between two phases. Okay, alright. Okay, so distribution coefficient or partition coefficient, okay, we can denote as K lah. We can denote as K. Okay, I write here as KP because I would like to focus on the partition coefficient lah. Okay, partition coefficient. Okay, at equilibrium, okay, when KP, right, KP more than 1, okay, at equilibrium there is more targeted component in desired phase than initial phase. The system is good for extraction. Again, this system I refer to the system, to two different system that have the same volume ratio, and then they have different type of solvent extractor. For example, here H2O, here is hexane, and here is CCl4 lah, carbon tetrachloride. Okay, so for example, at Kp more than 1, Kp is mean that there is more targeted component in the second phase than the initial phase. It means that the system is good. Okay, when Kp equal to 1, there is an equal amount of targeted component in both phases. Okay, so we can imagine like this. Okay, for example, here is you have, for example, you have 6 particle over 2 particle. Okay, so that is Kp larger than 1. It means in the targeted phase or the second phase lah, usually you want to extract, so it has more particle, more components than the initial phase. Kp equal to 1 is mean that you have equal distribution of particle lah. Okay, right. Okay, and Kp less than 1, okay, less than 1 is at equilibrium, there is less targeted component in desired phase than the system, okay, which is not the best for the extraction lah. Okay, so here for example, you have 6 over 2 over here. Okay, so if you look over here that Kp more than 1, okay, larger than 1 is our targeted lah. So usually if you want to try to extract something, you need to try to look the partition coefficient of that particular compound on particular solvent system. Okay, later on we will look into that. Okay, right. So as I already mentioned before, okay, about we can calculate the effectiveness of the system by calculating the partition or distribution coefficient. Okay, or we can denote as SK. Okay, when a solution is shaken with an immiscible solvent, it often dissolves in both layers lah. Common partition or distribute themselves between two layers. Okay, so usually when we create a separation system, we will create at least two phases lah. Okay, so partition refer to the distribution of particle between two layers lah. Okay, so for example, here. Okay, when equilibrium is reached, the ratio of solid concentration is in each layer is constant for each system and is denoted by K. okay, called the partition coefficient or distribution coefficient. So when equilibrium is reached, okay, we can calculate the ratio of concentration. Okay, that is what we refer as the partition or distribution coefficient. Okay, right. The key difference between partition coefficient and distribution coefficient is that the partition coefficient refers to concentration of an ionized chemical species of a compound, whereas the distribution coefficient refers to the concentration of both ionized and ionized chemical species of a compound. Okay, so because we have two kind of coefficient over here, partition and also distribution coefficient. So I would like to explain to you that partition coefficient, okay, specifically we use to calculate the ratio of concentration between unionized species. Okay, that is for partition coefficient. About distribution coefficient, it's actually calculate both ionized and unionized chemical species. Okay, that is the difference between partition and distribution coefficient. Okay, later on we will look into detail the application, okay, of partition and also distribution coefficient lah, where we can apply, okay, in the real application. The two term partition coefficient and distribution coefficient are usually used interchangeably, okay, because both these terms nearly express the same idea. Okay, it's about the same idea about distribution of chemical species between two mediums lah. Okay, so both of these two, okay, can be used interchangeably because it's refer the same idea lah. Because we want to know the distribution of chemical species between two medium lah. Okay. However, these terms differ from each other depending on the chemical species we are considering in the calculation. Okay, depends actually on the application, where we what kind of analyte we would like to extract. Okay, if our analytes, okay, can be in ionized and unionized species, so we go for the distribution coefficient calculation. If, for example, we say that the compound will not get ionized, okay, or we change the system to non-ionized, for example, the compound is ionized, okay, it's okay. So maybe we change the pH to make them unionized again. So we can use partition coefficient formula lah. Okay, basically they have about the same chemical formula. Not chemical formula, sorry, the K formula. Okay, alright. So we need to know that the partition or distribution coefficient is constant. Okay, the value is constant. Okay, the value is constant. Okay, for example here we would like to try to extract morphine. Okay, so if you look over here, okay, for example, if we use 50 to 50 ml water, okay, here we use 25 to 50 ml water, right? So if you look over here, regardless the volume, the K value should be constant. Okay, should be the same or similar or close to each other. Okay, they should be the same. Okay, here, okay, is why I'm saying that I want to stress another thing. Okay, it doesn't mean that if, for example, your K is very good, very large, that you can have a very good system for optimal extraction. Okay, this is a next system that I would like to discuss. Next type of system. Okay, so where you can apply different volume of extraction solvent, where you can apply different pressure or different heat, also a lot of factors. Okay, so previously as discussed on the same variables, only the solvent is different. Okay, now, okay, we would like to look at two different systems with two different, at the same solvent but at two different variables. Okay, if you look over here, okay, we use the 50 ml acetate to extract the morphine in this first A system, okay, while at the B one we choose only 25 ml. Okay, even though they have the same partition coefficient, distribution coefficient, partition coefficient. Okay, if you look over here at 25 ml ethyl acetate, let's say for example, the second phase is your desired phase lah. You want to inject in the HPLC, you want to inject at the GC, for example. If you look over here, okay, only small amount of particle inside here lah, okay, compared to this one. Okay, right. So let's say for example, okay, you directly inject this one, okay, you get about 0.06 molar. If you inject directly this one, you get 0.105 molar. Okay, let's say you have another step. Okay, you want to standardize the volume. Okay, you extract this first and then you add another 25 ml of acetate. What happened that your concentration here will be reduced about half. Okay, alright. Okay, let's continue. Okay, I just want to explain you about a thing. This is just, I'm not really sure if it will be related to us in the next few slides or in the next few chapter. Okay, but it's just a kind of the explanation that actually the student kind of mistakenly understand about this. Okay, let's say you have chemical over here, and then you have, for example, you have maybe here we have about 6 liter, okay, in volume, not 6 liter lah. And then you have, sorry, and then we have that 6 particle over here. Okay, so right now I would like to try to explain to you about the differences between mole or particle number over VS lah, over the concentration. Okay, because I don't want you guys to get confused, right? Let's say you have 6 particle in 6 liter, you get about 6. For example, we present the number of particles as mole, 6 mole per 6 liter. Right? What happened, for example, if we divide it to half. Okay, half. Okay, what happened to the number of mole or particle over here? Okay, it will reduce to 1, 2, 3. 1, 2, 3. And then what is the number of volume over here? It's divided by 2, of course it will become 3 liter. Okay, if you look over here that the number of mole, okay, is difference. Okay, after we divide them. Here we left with 3 and another with another 3 particle or 3 mole number. Right, how about concentration? Okay, it's supposed to be 3 liter per 3 mole per 3 liter or 3 mole per 3 liter. So if you look over here, okay, 6 mole over ni is equal to 1 mole per liter. 1 mole per liter. It means that even the number particle is reduced after we split into half, but the concentration will remain the same. Okay, because I have seen your seniors, okay, in the FYP project, they thought that if they take half, okay, they take half and put in another container, the concentration will reduce to half. Okay, it will not get reduced unless after you separate them into half and then you add solvent, 3 liter of solvent. That is the different. That is another story lah. This another story. Yes, the concentration will change. Okay, if that happen. Okay, so if let's say for example, sorry, we will go into that later on. Let's say for example, okay, you have 6 particle over here and then you add another 6 liter into the system. Will the number of particle change? No, the number of particle will be the same, right? So the only change about it is the concentration. Okay, 6 mole over 6 plus 6 liter lah. Okay, so you get about 0.5 mole per liter. So this is the concept that I think just a revision for us lah. Just a revision for us, so you guys not get confused when I mention about particle number, when I discuss about the concentration. Okay. Now let's look at the partition coefficient. how to calculate them. Kp is the ratio of concentration of unionized compound between two phases. I think I already discussed about that many times. To measure the partition coefficient of ionizable solids, pH of the aqueous phase is adjusted such that the predominant form of the compound is unionized. So if, let's say for example, your compound can be ionized, so you need to test either the pH. Okay, for example, you want to calculate for unionized compound lah. Okay, but for example, you test the pH of the solution is, for example, at 8. The pH is at 8. Okay, so when you do the study at a pH of 8, so they will ionize. So maybe you try to reduce the pH to, for example, 3, where the condition of the compound is unionized. So you can do that. Okay, let's say I give you this situation. Okay, what will you do? For example, the compound is ionized at 8. Okay, so you need to discuss that. Okay, by using by improving the pH by adding, for example, sodium hydroxide, adjusting to pH of 3, so we can start using partition coefficient. For example, I give you situation, can we calculate the partition coefficient, okay, at this condition? For example, at pH of 8, the compound start to ionize. Okay, you need to answer yes or no. How you can improve the situation? Okay, alright, that is the example lah. Okay, so you need to understand. So A1 A original A, right. Okay, now let's calculate the K. K, right? K refer to A. Sorry. Okay. K refer to partition coefficient. Ka refer to concentration. Okay, let's say here is A1 lah. Okay, I don't really like to use A1 actually. Okay, but it depends to you lah. Okay, but A1 refer to where we the desired phase. Okay, you want to extract. Okay, A2 refer to initial phase lah. Okay, so initial phase, and A1 refer to the final phase. I'm not sure why they use the term A1 or A2. Okay, maybe they want to refer, okay, this A1, A2. Okay, right, so it's very easy. You calculate the concentration in the first phase, and then you calculate, not the first phase lah, in the desired phase, and then you calculate the concentration in the initial phase. So you divide that, then you get the partition coefficient. Okay, if you look over here, okay, concentration can also be denoted as W over molecular weight. So you will get MW stand for molecular weight, WA stand for weight lah. W over stand for weight. V for what? V is for volume lah. It's for volume. So weight over molecular weight, you get what? You will get mole lah. You will get mole. Mole over volume, what is it? It will be concentration, mole per liter, for example. So supposedly it's about the same. Okay, let's say I would like you guys to please derive this equation to Kp or Kb lah. So you need to be able to understand. It's not that hard, right? A, okay, equal to mole per volume. Mole you can change it to Wa over M over W. You will get that thing. Okay, so if you look over here, okay, A over A, okay, we can denote as K, cannot maybe. Okay, so as dWA over WA2, okay, or desired phase over the initial phase. Okay, but for V2, okay, it should be in reverse lah, because yeah, you can use you can do the math by yourself. So when we try to simplify to this one, supposedly it will get reverse lah. We'll get reverse over here. Okay, if the volume is the same, okay, you can just neglect them. If volume is not the same, we need to include them lah. Okay, right. Usually we don't really neglect the volume, because if, for example, we use the system like previously lah shown. Where is it? This one, right? They have different volume. Okay, so you need to get the idea lah. Okay, alright. Okay, so if you look over here, in this formula as well, they can they actually remove the molecular weight, of course, because molecular weight between the first phase and second phase, we refer to the same analyte, supposed to give us the same value lah. If it's a different value, for sure that your calculation is wrong. Okay, we always refer to the same compound or component, so we can remove the molecular weight from the formula. Okay, so it will left us with the weight and volume. Okay, right. So that's how we can derive the equation. Is it important to derive the equation? I believe that if you understand, okay, I believe that if you understand, you can derive this equation. Okay. Alright. Here is the system. Okay. I think the figure is quite misleading. Supposedly, it should be presented by the same particle lah, not the pink and also the yellow one. It's supposed to be pink lah. Let's say they supposed to have, maybe here is different color lah. Maybe here is green colors. Okay. We cannot compare the distribution coefficient between different analyte. Okay, we need to compare the distribution coefficient of the same analyte, but we can use different system. Okay, like I said to you, H2O, here is benzene, here is hexane, here is CCl4, and our analyte is benzene, for example. Okay, so if you look over here at the first system, because of distribution on the desired phase is not that much, we should obtain small kp lah. And here, if you look over here, particle distribution is much higher on the desired phase, okay, or the final phase, and then we get large kp. Okay, that's how about it. Alright, here is the example lah, where okay, I don't think that is an accurate example for what I just explained to you, but here I just want you guys to understand. For example, if we have the same system, okay, octanol and water partition coefficient, octanol water partition coefficient. For example, this particular system is effective for benzene, okay, 2.13, but less effective for phenol extraction. Okay, this is another example lah, but using different kind of analyte we want to extract. Okay, if you look over here, this particular system is effective for benzene but less effective for phenol lah, but still effective lah, 1.46, nothing wrong with that. But of course, for benzene is quite good. Okay. Okay, now let's look at the distribution coefficient. Okay, as I already discussed, KD refer to both unionized and ionized compound between two phases. Okay, phases can be either between two liquid, or it can be either between liquid and solid lah. So when I refer to that particular term, it can be referred to both, either is liquid both or liquid and solid. Okay, so KD is measure of differential solubility of the compound between two phases. Distribution coefficient are used for example in estimating the distribution of drug within the body. So this is the example lah. Usually when drug, okay, we consume is in the base form, okay, but it can get ionized when it's enter our body, especially when it get to stomach, our stomach, where in our stomach is acidic, right? So distribution coefficient is useful in that particular example. So I think that's it. I will stop the recording. Okay, this is all for the part A. I will continue on the part B on this particular topic, and I will give the video by next week lah. Okay, so please watch this, all of this, and then we will have the discussion lah in the discussion session this particular Tuesday, if I'm not mistaken, right, our class. So that's it, I think. Alright, thank you so much. Okay, if you guys have any question, okay, we can discuss over there. Okay, I will do some activity as well. Thank you.